Han Yu and Wan Yi and Dr. Yu, okay, who is here. In fact, that's all of our own whole team. Okay. And Henry is assistant professor, and Dr. Yu is associate professor, and these two are our students. In fact, one of them already left, okay, working in California. And for the past 2 days, first of all, I have to thank you very much, okay, for the organizer or attendee invite me to give the opportunity to make this presentation. And for today, we learn a lot, okay, especially talking about metagenomic assembly, mission impossible. So I was wondering whether I should give this presentation at all, because I'm talking about assembly. So, but since Tom Cruise is doing that, I'll learn from him. I will take up the mission. Okay, now the goal is we want to find longer contigs for downstream analysis, not exactly assemble the whole genome. I think this is difficult even for a single genome. And the first talk I remember, okay, Mayer mentioned that when you're doing the assembly performance, the small k, there are many short contigs. And when you go to larger k for the Boundary graph, then the longer contigs, okay, for the high abundance ratio, but the low abundance ratio even shorter too. And as a bonus, I will try to explain the phenomenon, why it's like this. And this is one of the byproducts, okay, which I'm going to do. I hope that I can give an explanation for that. So the problem we are going to look at is the input is a set of short reads generated from a metagenomic sample, which can be human guts, ocean, water, etc. And the output will be just a set of contigs used for later analysis. Okay, for example, gene prediction, binning, or clustering, or annotation. So this is an example, okay, of the microbes, the abundancy profile of the microbes. This pie chart represents the genus level decomposition based on 16S RNA. Some of the microbes, okay, I hope I can work. Did you see it? No. Not working. No battery probably. So, for example, this microbe had 35.1%, and this bar is an expansion of this 6.2% of this small group. So this microbe can be only 0.1%. So you can see the abundancy difference can be about over 300 times. And if you look at the species level, can be even larger too. And this is the kind of abundance profile of the samples we are going to deal with. And what are the difficulties? Even the single genome, we have short, as mentioned by Mayer, that we have short contigs, we have branches and gaps. If you want to use it, that's the button. Oh, this is the thing. Okay, thank you. Okay, good, thank you. And the multiple K and error filtering is our approach to handle these short contigs. And this is implemented in our IDBA. And for metagenomic assembly, we have more problems. For example, we have different abundancy, which range, for example, 300, okay, difference. And also the sequence similarity. For example, the causes species are very similar. And we try to approach using progressive depth and local assembling for the similarity. And this is implemented in the IDBA UD. And for the consensus representation, which I heard this afternoon too, we have a meta IDBA to handle it. And unfortunately, these are two independent software. We don't have time to combine it together, but we will mention the idea, how we handle these problems. And at the end, we will look at about the binning, how binning help to do the assembly. And we will mention a little bit about transcriptome too, which we did a lot of work recently about the transcriptome and metatranscriptome. And one of the recent work we'll present next week is the recom, about the metatranscriptome. I will mention a little bit about this. So this afternoon, we had some people describe about the de Broglie graph. Brian, is it? I forgot. Yeah. Yeah. About then you break up, the read into k-mer, and the edge between two k-mers, if they appear in the same read and overlap k-1, and the symbol path will represent the context. So I won't go into detail of it. For example, this read can break down into 3 k-mers, and they join it together. And this is another read. You can make it continue, make it more k-mers, and eventually, these reads will represent a simple path, and this will be produced as a contig. This is the basic de Broglie graph approach to solve the assembly problem. Now, let me look at this approach, de Broglie graph. These are the reads, and assuming this is a genome, and we built the de Broglie graph as what we described before. This is k equal to 5. So this is a 5-mer. Each one of them, this is one is represent, basically from the reads. And now you can see that we have a problem. You got a branch problem here. The branch problem, because of you got a repeat over here. TACTA and TACTA, the same 5-mer appear in the reads, in the genome, and that's why you have this one branching over here. And this is the problem. In fact, if you want to look at simple path for the context, you have to get only very short context. And that's the reason when you got branches, then you have short context. What about if you look at k equal to 6, just increase k by 1, you construct a de Broglie graph. Now the branch is gone. Because the 6, you do not find a repeat pattern of 6 in the genome. So there's no branches. But unfortunately, you can see that there's no link between these two k-mer, 6-mer. The reason, and this is the gap problem. The gap problem is due to a missing read here. Because you can see that if we have TAC, then we should join these two k-mer together. But because we're missing one read, because the coverage may be low, that's why we got a gap over here. And that also explains, this is the result. You use the de Broglie graph, the k, the value is very important. If you use a small k, you got many branches. And that's why you have very short, context. And when you want a large k, you got lots of gaps. It may be okay for the high abundance species, because you may have the gap will not be that serious. But for the low abundance, then you got gaps, and then you will not have a long context again. So IDBA, is the idea we introduced. In the previous conventional assembler, they try to choose one k to balance both. Either you have branches or gaps. Depending on the abundance, they may choose a higher k with the abundance is high, a lower abundance, a lower k. But still, they cannot be doing all things. But IDBA basically is going to to use all k. What you're trying to do is you start with a k equal to 5. You construct with a branches over here. So we make these are the contigs produced by k equal to 5. After k equal to 5, what we do is we combine these contigs with the reads to run it again. Okay, equal to k equal to 6. You run it again using the reads and the contigs. Now you can see that there's no gap problem. The branch is gone too because it's 6. The reason is because this contig here is from the original, from the 5, give out the information, because you can see that 5 have no problem with the gap. And now we run this thing again, then we can get the contigs. Okay, the whole contigs. And so the basic idea is we run the assembler, the body graph, from small k increment into higher and higher k. For small k, you solve the gap problem. And then when you go to higher, you solve the branch problem. Then we try to solve both problems. And we expect that our IDBA will have longer we have a longer, it seems to be I can do it without the mic. I didn't notice it. So we can have the large k to solve the branch problem. So we expect that we have a longer contigs in this way. Now, when I look at it, when I look at the Bonney graph, I ask a question: why this is very counterintuitive? You try to break up the read into small parts and assemble it later on. What's the purpose of that or this thing? In fact, the example I gave out is no error. But if you got errors, the Bonney graph will be helpful. Let's look at this example. Okay, consider a data set with 30x and 75 base pair and 1% error. You can see that at simple calculation, you can see more than 50% of the reads have errors. If you look at the KMA, then 80% of the KMA are incorrect. Or I didn't write down what the KMA we use here. But you can see that more KMAs are incorrect. Okay, if you use that. And the error reads will create a lot of incorrect. Because you got error there, you got many incorrect vertexes. This is an example. These are the reads, and these are 2 errors. Okay. Now let's try to look at build a Bonney graph with this error there. So I'm talking about 7-ma. Now you look at this CAT, and also you do have, because of the error, you do have another KMA with an error here. We know that this is wrong, but we don't know it at first. Okay, we just look at the KMA, and similarly we look at another KMA, 7-ma. Then you can see that you got two error KMA here, and then you go on again. Okay, just an example. In fact, you can keep on doing it. Now you got another error KMA, and these are correct. Now you see that the error 7-ma is more than the correct. In fact, you keep on generating more error KMAs. But how do you tell which one is the correct or incorrect? In fact, that's the whole reason. If you got error, you throw the error rate away. Even you throw the error rate away, you are not gaining anything. Even you know which read have error, you won't gain anything. Because this read, even you got error here, you still contain information of those non-error base pairs. And that's the reason it's not good to throw it away. And that's why it's better to break it up. You break up this read with mistakes, you still can use some KMA which are correct. Okay, even though you can sacrifice this is wrong. Okay, now how can we tell it up? We look at the multiplicity. because the correct k-mers appear 4 times, and this 3 times, and this 4 times, and this only 1 time. And we can throw this one with single multiplicity, say that they are error. So this is the filtering. The error k-mer can be filtered by single multiplicity easily. And then this will induce the incorrect. You build a de Broglie graph using the k-mer, you throw out the incorrect k-mer. And then it's not only make the algorithm simple, you reduce the memory requirement a lot and make it more efficient. So this is the way we use de Broglie graph is the benefits. Now, this is a short summary. Single k and error filtering. This is then you have the problem is small k, you got many branches, and you have more and shorter contigs. And when you got large k, the branches resolve but more gaps, and longer contigs for high abundance species because the gap problem will not be serious. But for the shorter contigs, for the low abundancy, you got even shorter. I think that is the Mayer trying to address why it's like this. Now you can see why the k make a lot of difference. And while IDBA use multiple k and error filtering seems promising, at least. That's the reason we try to use IDBA to start with. Now let's go to the problem with the single genome. We have IDBA, but now let's go to the metagenomic. Metagenomic assembly. We have. Did I show this slide already?
Yeah, but it's okay. You can.
Okay. Why is it here again?
Yeah, because I want to emphasize the 2 problems.
Oh, yeah. Now, for the metagenomic assembly, because I prepared this thing last night, and now I forgot, confused which go to which. The metagenomic assembly, we have 2 problems: different abundancy, and also sequence similarity. And we are going to discuss, how to solve this thing. This is only for single genome. Now, the error filtering will fail for species with uneven abundancy, depth of range. Now let's make an assumption. High abundancy 35%, low abundancy 0.1%. You got 1 G data and assume the genome is 10 meg. Just assumption. Then the coverage vary from 350 to 1. And assume the read length is 100 and 1% error rates. Then the way you sample, a read from the low abundancy, even if it's correct, you can calculate the probability 999, because 1% error, or every B pair is correct, and because coverage is 1, so about that much, that number is the rate of getting a good, a correct read from a low abundancy. But if you look at the error reads from a high abundancy, then you can see that this is more than the low abundancy correct rates, because now you can see 0.1 is the error, because you can have free position you can change to, free B pair, and you got 350, so it comes to be larger. So the conclusion is the number of correct k-mer from the low abundancy is maybe less than the number of error compared to abundancy. That means the abundancy will give you more error, can be more error k-mers than the correct k-mer from the low abundancy one. So the implication is multiplicity for a correct k-mer may be less than the multiplicity of an error k-mer for the high abundancy, because high abundancy can give error. So using a threshold to filter out the error k-mer will not work, because the difference in abundancy. Then how can we handle it? And because we are doing collaborative, I would like to invite Dr. Yu to help me, okay, to make the next half of the presentation.
Okay. I'm not helping.
No, he can do better job than I. He always get the best teacher award. Okay.
Thank you. Okay, I think the main reason is Professor Chin worried that everybody will fall asleep, after half the presentation. That's why we switch. And then at the end, I will switch back to him, so that hopefully you will not fall asleep. Okay, so anyway, let me recap a little bit. Basically, this is like a mission impossible. So we are not going to solve all the problem in the metagenomic assembly problem, okay? But on the other hand, we try to highlight some of the issues that we discover and then share with you our solutions. All right, so the first problem is, as Professor Jim mentioned, okay, if we use, there are many error chimeras in the sample, in the graph. So if we only use a single threshold to remove all the error chimera, it won't work because of the, the main reason here. All right, now let me give you a very simple example. Now you can see that the yellow one are the correct vertices, and the red one will be the error vertices. Then you can see the red and the yellow are, interleaved together. If you look at the multiplicity of those yellow vertices and the red vertices, sort of you can see that they all mix together. In particular, I want to bring to your attention this context. Actually, this yellow one is correct, but it's from a low abundancy species, right? So you can see it's like 4, 3, 5. But then on the other hand, you got error with multiplicity 3, 2, etc. All right. Now, so if you use a single threshold to remove it, if you set the threshold very low, it might be still okay. So you can see if we set the threshold to be less than or equal to 2, then this error will gone, this error will gone. It seems good, right? But then if you try to use a different threshold, 3, then you can see that some part of the real correct context gone, all right? And so on and so forth. If you use 4, 5, and somehow, you can see that those low abundancy contact or vertices will also be removed easily. All right, so it gives you a very simple example that no single multiplicity will work. All right. Now, so let me just illustrate our idea. It's also very simple intuitively. So what we do is we try to do it progressively. All right. Now, so we try to start with multiplicity less than or equal to 2. All right. So we remove some of the error vertices. And then what we do is, you can see that these 3 and 5 become a single path. So what we do is, we try to recalculate the average multiplicity of a single path. The reason behind is, as long as this is a long single path, even the multiplicity is low, we assume that is correct. All right. Now, so you can see that we try to update the multiplicity, become 4, and then we try to remove 3. All right, and then we calculate the multiplicity again. Then you can see that now this low abundancy contact will stay. All right, luckily. Okay, and so on and so forth. And then of course this example, we purposely make it to illustrate our idea. Then you can see that after the removal, we have only the correct vertices here. All right, so this is the basic idea behind the progressive depth removal. Now I want to emphasize that when we put in a real situation, we are able to keep some context with low abundancy, but however, we cannot solve the problem completely. If you really understand our approach, you can see that we also will remove some of the correct chimera if the multiplicity is low, right? So in other words, we didn't really solve the problem completely. For those extremely low abundancy species, actually, it's still an open problem, how to get it out. All right. Okay, now then I move on to the second difficulty for metagenomic assembly. Now this is, I think everybody sort of understand the difficulties, right? But we try to look into the issues in more details. Now this is basically a sequence similarity problem. And in fact, we are talking about 2 kinds of a sequence similarity. Now, the first kind of sequence similarity is we have different species, right? But different species, they also have similar pattern in the genome. All right, so you make the graph very complicated. But on the other hand, we might also have subspecies, right? Okay, then this also create another kinds of sequence similarity issue in the graph. Okay, so we try to talk about this one by one and then also share with you our solutions. And now this table only want to give you some idea. We try to do a statistics using k equal to 50 for different taxonomy. Then we find that even for the species level, you know, they have many common k-mers in different species. Then you think about it, if we have a sample of metagenomics, and then they have this kind of species inside the same sample, then you can see the graph will be very complicated because they have too many common k-mers. Okay, they are the same. All right, so this basically contribute the difficulty of the first problem. So we have, you know, the same common pattern in different species. Okay, and the impact basically is like this. Okay, we make this up. Okay, so that hopefully it's easier to understand. Then you can see that we try to do the contact. Usually, the basic principle is when we have branches here, then we stop the contact here. Then you can see the graph here is so complicated, right? Now many assembler, what they do is they may try to enumerate the possible path here and then use pair n data to support which path is good, which path is bad. But in the real situation, there will be too many possible paths. Okay, so it becomes computationally difficult to enumerate all of them. All right, so this is basically the first problem. Now, so what we do is also not very difficult. The idea behind is, again, use the pair n data. Okay, so you can see that this is trivial, right? If they belong to the same pair, they must come from the same genome. All right. So what we do is most of the assembler try to use the pair n data to do the scaffolding. But what we do is we try to use it directly on the assembling. But if you look at, you know, those more recent assembler, in fact, they also use the same idea too. All right. In fact, our multiple K idea has also been adopted in other assembler as well. Okay, so what we do is we do not enumerate all the possible paths. We try to consider a subproblem because we know that most of the edges here does not matter. I mean, it's not related to the single genome. So what we do is we try to identify all the pair n reads so that one of the n belong to this contact. And then we try to identify, you know, which edge, which vertices the other n belong to. All right, only identify those subset of reads and then do a local assembly. In fact, we also want the IDBA or locally in this subproblem. Then effectively, you can see that we might be able to extend the path a little bit. And then we keep doing this until we are not able to extend it further. Then we stop. And then it seems the result is quite good, so we are able to get a longer context in this way. So we call this technique the local assembly. Okay, now here it will be some of the experimental results. It's pretty old because we didn't update it yet, okay? But you can see that if we try to compare soup, vervid, we have fewer contact, and then the N50 is larger, coverage is good, and the error is fewer, okay? We have fewer errors. And this will be the real data. Then you can see we have a similar better performance, like we have a better N50, longer, and then, you know, because this real data, we do not know the exact genome, so we try to align the contact to the genes, and basically we can identify more genes than the other software. So this basically concludes the first type of similarity problem. Okay. Now then I proceed to talk about the second similarity problem, because in a metagenomic sample, then you can see that we have subspecies. Now the problem getting more seriously, okay, because subspecies usually they are more similar. All right, then the implication is in the graph you are going to have even more branches. Okay, and let me see whether I can give you some feeling. Okay, now then you can see that we do a very simple exercise. Now here we are talking about E. coli. There's only one subspecies, and then we try to mix 5 subspecies in the same graph, and then we fix k equal to 50. Now you can see that the number of k-mer, the vertices in the graph has gone up by about 3 times, right? So the number of vertices go up by 3 times. But on the other hand, if you look at branches, the original graph with one subspecies is on 800. but then it become like 130,000. So it's more than 100 times. Yep. Question genome. We make it up, simulated. Okay. Just want to look at the graph without error. Even without error, it's like this. Okay. And then we try to run, the standard Vervid, R-based sub de novo. Then you can see that when they put in this subspecies case, the performance degrade a lot. Okay. For example, you can see the number of contact increase a lot because the length of the contact drop dramatically. All right. And of course, I want to talk about IDBA. Seems better, right? But still, we cannot solve the problem completely. That's why it's mission impossible. All right, now, I also want to, this is real. Actually, this is one part of the de Bondy graph constructed based on subspecies. You can see that there are many branches here. All right? Now, we try to look at the actual sequence. Probably you cannot see it clearly, but if you look at it carefully, it seems like there are many common paths, and then there are some variation like insertion, deletion, substitution, all over. All right, so that's why it come up with a graph like this. Okay, now but the problem is even they are similar, they are not error, right? But they are not very similar. So those kind of bubble removal things like that, it won't work. Okay. Now on the other hand, you may ask me, then how about your local assembly techniques? Now, it still won't work because usually this variation will not span very long because they are very similar. Okay, so that's why when you compare the insert size of a parent data, the pair n, the local assembly will not work because of the one end is on the contact, but the other end is already go over to this subgraph already. Okay. So our question is, do we really want to separate them because they belong to subspecies, right? I remember the talk in the earlier day. Actually, he used the same approach as us. We do not want to separate this kind of subgraph because they belong to the subspecies. So depending on what question you want to answer, all right, we may try to represent the whole thing, whole subgraph together if they really belong to subspecies, all right? And the second question is, you remember that we do have other branches. They actually come from different species, right? Now, so in other words, in the graph, you are going to have two types of branches, right? One is due to the different species. The other is due to the the pattern, the common pattern of subspecies. All right? Now, so what we want to do is, of course, we want to remove or delete the branches that is due to different species. And then on the other hand, we want to keep the branches of the subspecies. Okay? So we have a question number 2. So how to distinguish a branch, whether it's due to different species or different subspecies? Okay, so altogether, if we can solve these two problems, we partially solve this kind of similarity problem in the metagenomic assembly. All right, so our idea is we try to convert the problem into a solution. So in other words, we do not want to remove the branches and caused by the subspecies. Okay, so what we want to do is we make it a 2-step. Remove the branches due to different species, and then you can see that we can separate the graph into different components. Okay, and then each component, we hope that it contains only subspecies. And then on the other hand, the second step actually is very similar to the meta-cortex that the speaker talked about this morning. We try to use consensus to represent the contact in each connected component. The main difference is we only output one contact, but they try to use a better method to output more than one context. Okay, but the idea is very similar. Okay, so the last part is how we can remove the branches due to different species but not subspecies. We base on a very simple observation. Now I told you if they are in species level, the amount of common chimer is a lot, right? Okay, in other words, the branches caused by similar subspecies will start from a common chimer, but then they will converge into a common chimer very quickly. Okay, let me give you an example. Maybe you understand what I'm talking about. Now, so we have 4 subspecies here. Now, this part is common. These are the genome. Okay, so you can see that they only have like 3 positions. They are different. Okay, then they will come back to a common pattern again. So in other words, the span of the variation part should not be very long. Okay, so if you look at the graph here, now when we search for the contact, we stop here because we got branches. Okay, then we try to keep track the branches when they converge again. If the distance here is very short, then we will assume those branches are caused by subspecies. will not remove it. And then we try to remove those branches that they go out, but then, you know, come back a long way, long path later. Okay, then we try to remove those kind of branches. Okay, then basically this is the idea. We try to resolve these problems. And I forgot, is it E. coli? Right, maybe E. coli. Then we try to get out this kind of components. They each represent a certain subspecies. But I want to emphasize it again. Then you can see that we have meta IDBA. We also have IDBA UD. In fact, the technique we feel that can be combined into one software. As Professor mentioned, we don't have time, right? We don't have manpower to do it. So if any one of you are interested, then we can talk about this, how to do the combination. Then come to the last part. I think they will be sleepy. So I give it back to you. Then we will end the talk.
Okay. In fact, we did some work about binning. And the assemble can help binning, but binning can also help assemble. And now the metagenomic, okay, assembly, we talk about progressive depth, local assembly, and using the consensus to do the subspecies similarity. Now what's binning? In fact, binning using different techniques. When you got reads, we want to put in the same bin, the same group. We believe that they are belonging to the same species. And what technique? They are not really making contigs. Okay, for example, when you got the contigs, you got branches, then the contig will stop. But the binning, they may put together because they are belong to the same group. As long as they are belong to the same group, so we look at the overlap of the reads. We look at the what? Also the former spectrum. Okay, I won't go into that. And then they are similar, and then we use this former spectrum to group together. And moreover, if they share very long path, they will put together too. So similar to the known reference genome, we put it together. And this method, we have a meta cluster. We build meta cluster on this thing and improve. So that we can improve the N50 by about 10%. Okay, we didn't look into very detail in it, but we know that binning can help the assembly, at least especially for the metagenomic. And in fact, we are using the meta cluster to do some of the things for the annotation, you know, which we are going to. And for the transcriptome, this is very difficult because the RNA seq and the genomic data, the RNA seq has more common pattern than the genome. And moreover, they have different abundancy because the expression level is already can be a lot, and also the coverage can be different. And another thing is splicing too. So we've got exons. Then you make the transcriptome assemble very difficult. And they have software like Trinity, Oasis, Warvet, you know, SC, and we have a T transcriptome IDBA, which is using the pair N to do the assemble. And this IDBA tran, okay, is using pair N and also try to deal with uneven expression level too. This is something more difficult, okay. And now let me give you some example, okay, about this is from the metagenomic. Now this is only from the single species. But now when you look at metagenomic, that you can see that the gene, okay, if they are talking about 40 length, maybe here, then 44% of the gene have the common pattern, and many of them are at the end too. 41% are common at the end, and the same as you can see, you go up with this length, it will be lower, but still quite a lot. Okay, even 10, 100, you got 23% of the gene are in common, and 50 at the end, and this will give me the trimerate. Okay, because you try to merge when you do the assemble. we got the problem. Now this is the common pattern, similar pattern, a lot. And the difference in abundancy can also be a lot, okay? Because the expression level can be 1,000 times and the abundance can be 100 times, can be differ a lot. This is another mission impossible. But so we align, okay, basically we have the MT, okay, the meta transcriptome. We handle the turmeric context. And now the paper we are going to present next week is on with the protein information, because with the mRNA is going to decode protein, and we look at the database, we got more protein information than the genome information. So different mRNA, but now the problem is different mRNA can decode a similar protein, but we use the protein information as a guidance for doing the assemble, okay, for doing assembly. So we align the protein to the de Broglie graph basically, and using because the protein is because you go to decode, we use the protein database information to help the assemble, and this is something we did, and I think that's finished our talk, and question and comments. Okay, Dandy. Thank you.
Yes, I would like to ask about the species versus subspecies. So for me, it's not clear what subspecies is. Species is defined with 16S. So I guess in a way you've defined. So what's your definition of a subspecies, or is that the definition that two things are the same subspecies as long as they don't differ by more than?
I think George can answer this better than I. You want to say something? George?
You cannot identify a species by 16S.
Oh no, but that's how they define that. That's the definition. That's
No,
not really.
I'm sorry?
What is the definition? What's the definition of a species?
The definition of a species as at the moment is 70% DNA homology and at least 96% 16S ribosomal RNA sequence similarity. But the real problem is that the 16S sequence similarity varies on a genus by genus basis. You can identify to the genus level at 96% plus or minus a couple percent and below. So some of the figures that I showed yesterday give you an indication of how well that test works, and it's not particularly robust. The issue of subspecies is that it's typically a variability in some phenotype that is readily identifiable that separates different varieties. But you have to be very careful because a subspecies is very similar to what's known as a biovar or a serovar or a phagovar. So I mean, it's just a small difference that's you can use for distinguishing the organisms, but you may or may not see something at the species level or even at the genus level that's going to be consistent. Somebody defined it, and then you have to worry about how you deal with it downstream. There are only about 450 subspecies, fortunately.
Thank you. Is it okay? I think it's okay, I hope.
But can you show that what you use as your definition corresponds to what?
We are more naive. We do not know those kind of definition. From our limited knowledge.
Working definition.
Like different strands. For example, E. coli, and then if you have different strands, then we assume that they are subspecies. So we just use these kind of simple definitions.
In many cases, right, you just mean clonal groups. There are many species in which there are clonal groups which you find in many different places, and those have been defined.
Right.
Okay,
That's it.
That's what you're. You don't really.
We don't get to very experts, definition of the species. Right. Yes.
More questions? Okay, well, thank you very much.
Thank you very much. Thank you.